Thank you very much, Clive. It's very kind. Good morning, everybody. Delighted to be here. And actually, I probably won't stick very much to my presentation because the discussion already has provoked a whole bunch of issues. And this picture on the front here actually goes back to a project I did ages ago, which is Part 2A related. There was asbestos cement fragments in the garden, and there was a great deal of dithering about whether it might represent Part 2A or not. And so whilst everybody was dithering, the household had got a rotavated the garden, dug up all the fragments of cement, put them in a big bag and took them down the tip. Now, I'm not saying that she may have exposed herself to a significant level of risk, but I think the answer was probably not, because this asbestos came from her broken shed roof, which of course we didn't think was covered by Part 2A. It wasn't actually in tatters, it was just fragmented. And at times we sort of overreact and we think we go and do an awful lot of work to get to an end point, when actually some common sense, and I think the current version of the statutory guidance allows us to start to apply a deal more common sense, a deal more sustainable thought to the need or otherwise for remediation. And the starting point of the new stat guidance is that you should assume that land isn't contaminated unless you can demonstrate, and when I say contaminated, the legal definition, unless you can demonstrate affirmatively that it is. But having said that, there is a huge driver, in my view, to get a proper grip on asbestos. If you were to say how many people have died in this country from arsenic exposure, the answer is we don't know, but probably not very many. Maybe it's a contributory effect to a lot of deaths, but that's part and parcel of living, isn't it? Asbestos, though, you can point to numerous cases where people have died from mesothelioma, from other forms of asbestos-related disease, which are associated with their exposure to asbestos in the workplace or in the environment, and so on. And so if you were going to actually decide how to spend your money on health improvement, you probably look at where the greatest number of deaths have been, or serious injuries, or ill health, and asbestos may be right up there with it. So I'd very much support the idea that DEFRA spends some future research money, David, there we go, on getting a better grip on asbestos. It's been far too long the elephant in the room when it comes to contaminated land. We know about it, we don't have any guides. The last guides we had was withdrawn, the old ICRCL stuff. And it would be great to see new guidance and new science actually supporting logical, sensible approach to asbestos. So, taking the risk out of remediation. Easier to say, harder to achieve. If contractors could go into projects with no risk, they'd love it, wouldn't they? They could just turn the handle and get lots of cash out of the project. Clients would love it. The job comes out, with great certainty. He knows what it's going to cost. He knows what he's going to end up with. And the third parties affected will know exactly what's going to happen. But of course, there are a whole bunch of uncertainties around the financial, technical programme and sort of third-party issues of remediation, and it's the monkey on the shoulder. And I make no apologies for the monkey business that threads its way through this presentation. I was actually sitting in an airport and had 5 hours to wait, so I just livened this presentation up a bit. Conventional investigation gives conventional results, and we're still working sometimes in the way in which we worked 20, 30 years ago, doing boreholes, taking samples, sending them to laboratories, getting the results back, and then discovering that we've got some massive data gaps. So, I wish I'd done a borehole there, I wish I'd taken that borehole 5 metres deeper, etc. So our site characterisation is limited, conceptual site models are flawed, and we haven't really got a clue as to exactly where our plume might be. And we end up, poor monkey, cost and time overruns, failure to complete the treatment, and certainly failure to get regulatory sign-off at times. It's not sustainable. And I think sustainability, although it's a concept that we talk about in very general terms, the actual specific application to site investigation and remediation can actually give you wins both on the social, the economic and the environmental fronts. You're not actually paying more money to get a sustainable outcome, in my view, generally. You're actually paying the right amount of money to get enough work done to solve the problem to the correct extent. So an introduction, I think sustainable practice starts with regulation. If the regulators are working in a framework which actually has built sustainability into it, then they will actually be in tune with the things that you're trying to achieve as a practitioner. We then go on to site investigation, and that's the basic tool for understanding what's there. All too often we walk into a site, we do a little bit of site investigation. Clients hate spending money on site investigation, don't they? It's all money gone into the ground, you can't see any benefit from it, there's no clean-up, there's no structures built, it's just money down the pan as far as they're concerned, so they like to minimise it. It's a very short-sighted attitude, because out of that site investigation you'll do your risk assessment, which says how much work you've got to do and where you've got to focus it. And if you've got woolly information going into that, you end up with a woolly focus, which means it's much wider than it needs to be. And then the remediation comes along, and the poor old remediation contractors trying to find where all this sort of solvent's gone into the ground, and it could have spread here, it could have gone down, it could have been floating. And they're on hiding to nothing sometimes, because they've got really tight contracts. When times are hard, when there's not enough work around, we take on terms and conditions which are not sustainable. They put huge amounts of risk on contractors. Contractors then behave in a very sort of adversarial way, trying to actually battle through a contract to make some money. If they don't make money, they go out of business, and then we have no remediation contractors, and that's no good for anybody. So we need to deliver remediation which balances environmental improvement and the social impacts of the work and the costs associated with it. And I don't believe these are incompatible. So in terms of sustainable approach to site investigation, I think the conventional techniques, and by which I mean boreholes and sampling and laboratories, don't give you the right information these days. And the main shortfalls are lack of sampling sophistication. So that monkey will only really understand the water quality at that very specific location. And if you could have a more sustainable way of taking water, you'd be all right. Constraints in obtaining water samples from precise depths in the ground. Now, there are now tools out there which we can take samples of water every 100 millimetres if we want, and get really good information on what's happening at depth. If we start using on-site testing systems, we can actually get real-time results, understand what's happening, and make judgments about the continuation of the boring or the sampling technique, and about where we're going with it day by day, instead of at the end when it's too late to go back and do something else. And challenges in understanding, the behaviour rock strata, which is about my first case study. But what I'm talking about here is a trial approach, which is a US sort of promoted idea. But it doesn't say you will use this technique or you will do this or that. Specifically, it says plan your work systematically, have a dynamic work strategy, which means that you can react to the data you're getting on site day by day and change the scope of your investigation to reflect the information you're getting and get that data in real time. Of course, that doesn't work very well if you have a client who says, well, draw up a bill of quantities, tell me precisely how many boreholes we're going to drill, and then go out there and drill them. That's not a dynamic strategy at all. And so what we need is clients who will help us or work with us to understand that a site investigation should be a living thing. It may work within a range of costs, but it's not fixed to a very precise bill of quantities which you have to deliver. And if you actually take that flexible approach, you can save a lot of money. There was a guy called Professor Ian White who worked at Manchester University, and I've been trying to get hold of him to see if I can get his paper, but way back in the sort of early 90s, he was giving papers where he said, okay, site investigation, typical amount of money spent on site investigation, more often for geotechnical purposes, was about between 1.25% of the capital value of the project to which it related. And the typical cost overruns on those capital projects is between 10 and 20% of the capital cost. If you increase your site investigation spend to between 1 and 2% of the capital cost, you actually reduce your overrun on the works by often down to very close to zero. So by spending an extra sort of 1.5%, you can save yourself 10 or 20%. And he had good data for that, and I'd love to be able to get hold of the paper and actually quote it in more detail. But I've emailed the emails I found on the internet but not had any response, which either means he doesn't like me or else he's not there anymore. Spend more money on investigation, spend less money on remediation. We call it high-resolution site characterisation. It's about understanding transport pathways, exposure pathways, understanding how what processes affect the fate of the contaminants, and understand the contaminants' mass distribution and so on, and then how remedial measures will affect the problem. And it's an investigation in which the scale of the measurements is consistent with the scale of the variability of the measure property. If you've got a nice uniform sand and gravel stratum with contaminants in it, you probably actually can characterise that fairly easily. If you've got a complex series of layers of different permeabilities and maybe overlying a sort of rock structure with fissure, fractured rock structure, then you need to actually have an investigation which can measure data at the scale at which your discontinuities and features exist. And the benefits are reduced uncertainty, much faster because you're working on site and you can get your investigation done all in one go. Health and safety risks reduced because you're on site for shorter periods of time. Cheaper SI cost for the equivalent amount of information. I'm not pretending that these techniques are cheaper than a conventional site investigation. But what I'm saying is if you wanted to use conventional site investigation to get the same amount of data, you'd end up spending a lot more money than if you go for it through a sort of a reactive system. And this will lead to reduced remediation costs, certainty of remediation performance, and sustainable for both the site investigation and remediation stages. Some sampling, as the monkey might tell you, is unnecessary. So, I was going to talk about 2 or 3 case studies. I'm dying to hear the sibilant tones of Clive's egg timer soon, actually. I was in China last week doing a conference, and they had this whopping great bell, and it scared you to death, when this bell went off. Yes. So the egg timer was much nicer and kinder. How much longer have we got, Clive?
20 minutes.
Oh, good. So, here was a site. There'd been an extensive traditional site investigation done on this site, and it cost £1 million. And when we were sort of asked to go and talk to this particular client, he said, I spent £1 million on site investigation, and I seem to have a very expensive remediation coming up, and I'm not sure if I'm using my money wisely here. I don't recall the last time we spent £1 million on a site investigation, apart from, let's say, a high-speed railway or some big sort of infrastructure project. So, eyebrows go up. Blimey, that was a lot of money. Went and had a look at it. Not too complex a sequence of sort of made ground over alluvium, over shale, solvent spillage over time. Area of impact wasn't fully defined, and the anticipated remediation at 10 million was all about pump and treat and putting in barriers. I hate pump and treat. I don't remember the last time I've seen a pump and treat which was truly successful, because it just goes on forever. And when do you stop? So we looked at this, we had a rethink. We said, look, we do need to do some more investigation because you don't understand the extent of the problem. And we brought in a series of techniques, Gauss-Orbers, which give you instant results, but in situ results for near the surface. The modified Waterloo profile, which we bring in from the States, or from Canada rather. And we did a deep fracture network investigation, which is all about rock coring and understanding the rock itself and the fissure, and the relationship between the water in the fissures and the water in the rock mass. At the end of our investigation, we agreed a remedial solution with regulators, which we were confident of delivering because we had to do it ourselves. And we priced that at a total of 2.5 million, including our investigation costs. And we've now finished the work for 2.5 million. So it's not a pretend number, it's a real number. In some ways, David, although it's not a Part 2A site, it could be a Part 2A site, but actually this client's taking voluntary action. And it's an example of using what I would call a sustainable approach to remediation, which comes up with a solution which is immediately given a 7.5 saving in that client's eyes. So all of a sudden your 140 million doesn't look so daft. Not that I'm suggesting it was daft in the first place. But it is about saying, actually, if there are very real potential remediation projects going ahead with a particular tag to them, you may be able to do something different. And we can all swing together in time. Oh, God. So here was the geology, and the only point in showing you that is actually, you know what it's like. You do site investigation, you hit the rock, and your conventional soil techniques don't go through the rock, so you're going to start coring. So our Waterloo profiler went down to the top of the weathered shale. We realised that there was something funny going on. The concentrations of solvent in the water in the fractures was quite low. It didn't seem to be too much of a problem, but it didn't actually stack up in relation to our sort of overall view of the site. So we took core samples, a lot of core samples, crushed them, and removed the pore water from the actual rock mass and tested that, and it had high concentrations of solvent. What happened was the solvent was absorbing preferentially to the rock mass, and it was obviously at its saturation point in the water. So if you just sucked the water out and pump and treat, all that would happen is that the solvent in the rock mass would then move back out into the next bit of clean water that comes into the fractures, and you'd be pumping and treating forever because you've got a continuous replenishment, as DNAPL does, of the water. So thank heavens the client didn't go ahead and do pump and treat, but actually a really aggressive treatment technology, in situ treatment technology, was where we had to go. So there was the Gauss-Orber results. We need to make some progress with these slides now. There's the Waterloo profiler inside the building, nice and neat. Goes on a sort of conventional rig and so on. On-site lab, so it's not just a screening lab. We had a full GCMS on site. We used off-site labs for correlation of results, but we used most of the data we got was on the on-site lab, allowing us to take those day-by-day decisions as to how deep to take the boreholes, etc. Then we had, this is the review of the rock core samples and the selection for testing. There's our lab. And here's some pictures of what we were finding. So TCE, the original solvent, in two areas principally. Every blob on those is a real data point, a real water quality data point. So we were pretty confident that we'd got the underside of the plume defined, etc. Cis12 DCE was the sort of breakdown product, and again more extensive as the solvent is changing in the ground. And then vinyl chloride again. So two main blob areas which look in plan like that. And our intention was two quite large areas of impact. We're going to steam treat those, a steam enhanced vacuum extraction. And some intervening areas of lower impact we were going to treat by long-term injection of biological substrate to encourage biological breakdown over time. But our problem with vacuum extraction was that we hadn't got any air to extract from. The clay, the alluvium, acted as a cap, and the groundwater below that fully saturated the shale up to the underside of the alluvium. So how can you vacuum extract? So we formed what we call a steam bubble. So we injected steam, which was actually generated by the factory that we were working on, so they already actually had a steam supply there. And we put in the steam under high pressure to generate a saturated void space beneath the clay, which we could then extract the solvent from. We warmed the ground up to about 90 degrees centigrade, which caused a huge amount of solvent to come out of the rock mass and into our vapour and out and through carbon for stripping and eventual re-injection of clean water back into the site. And the carbon went back for regeneration with the solvents in it. So that steam bubble was proved to be pretty successful, a bit scary at times. Health and safety issues around using steam are quite substantial, so I wouldn't recommend doing it unless you're quite confident about what you're up to. A series of thermocouples used to actually measure the temperatures that we were generating in the ground. One of our challenges now is to get it to cool down. There's no point in injecting the biological substrate into the ground until you've got back down to a temperature where the bacteria can survive happily. So we're talking about getting back down to at least below 40 centigrade, and that's happening over time, but it is quite slow. So there was our steam infrastructure injecting into the ground. I should as well absolutely acknowledge that QDS were the specialist contractor who was doing the hands-on work here, and we were the turnkey contractor overseeing it and working with QDS on that one. Vapour treatment system, let's move through these. Liquid phase treatment system, so all fairly sophisticated. but all for 1.9 million. What a bargain. And this is the mass recovery curve, so you can see here, if you can see that enough, a ton of solvent out over time, and then we started to get a flattening of the curve. And we agreed with the regulator that, with the law of diminishing returns, that we wouldn't continue to persist to try and take out very small amounts of solvent at a much greater effort, a sustainable point at which to stop. And we're obviously also monitoring recovery subsequently. So, long-term pump and treat was rejected on cost and time scales, and it wouldn't have worked anyway. In situ treatment was achieved, outturn cost 2.5 million. That I think is sustainable, and all the monkeys were happy. But was it sustainable? You know, what about little baby monkeys in the future? From an environmental point of view, in a year we were able to effect the rapid and fairly substantial removal of pollution from the ground. And we know that the investigation had a lower carbon footprint than if you had done it by an alternative means. We actually did a carbon assessment of a conventional investigation to get the same data as the investigation we did. Ours came out at about just over 20 tonnes, and the conventional one would have been about 30 tonnes. We haven't finished the carbon assessment on the remediation yet, and one of the things there is steam. You know, if we actually include steam in our remediation carbon assessment, then that's going to actually reflect a lot of carbon being used to generate the steam. But it was already there on site, it was already being generated by the client for the actual operational purposes, and we were taking the excess steam. So do you count it or don't you? I don't know. But you've got to recognise that issue exists. From a social point of view, the neighbours hardly knew what was happening. You know, it really didn't affect our neighbours. There were very few vehicle movements, and all sort of emissions were captured using carbon and treated and so on. And from an economic standpoint, it was 25% of the cost of the alternative approach. So it seems to sort of, you know, work on all sort of three columns or legs of the sustainability stool. Two more short case studies, and I'll leave you in peace. So you're going to give me a 5-minute warning? Yeah, right, okay. So this is in Ireland. Again, a previous investigation, 40 locations, another 4 wells down to 70 metres, and it was all about how extensive is El Napel. We did a series of pieces of work around using this rapid optical screening tool, which is sort of laser-induced system using a conventional push probe rig. And taking discrete samples. So there's our rig, it's a good old Fugro rig, does Dutch cone, does all sorts of push tools, but it's a laser-induced fluorescent sensor on the end of the tool, which tells us where the hydrocarbons are on a very sensitive basis. And we were able to characterise the subsurface very effectively. We did about 58 locations, you can see there. I don't know what the blue blobs are. They were the deep boreholes, sorry. And then we ended up with a conceptual model that showed actually that there was El Napel floating on the surface of the groundwater, the blue line, but there were also some deeper preferential pathways where some D Napel was going. But we were also able to show that, I'll just pass over these little graphs because I can't read them either. We were able to show that the conditions in the ground were conducive to natural degradation of the El Napel, and that actually in terms of its distance of travel it would probably have reduced to an acceptable concentration by the time it got off site. And we actually agreed with the regulator that although we would do some remediation of soils on the site, we wouldn't have to do any groundwater cleanup because it would effectively take care of itself by more natural attenuation. So client had a provisional original estimate on this of 2 million for remediation. We reckon by the time he's paid for our high resolution characterisation at 300,000 and some soil remediation, some soil removal, he'll be looking at a bill at around about 1 million, I think it is. So again, a good outcome for him. And the regulator's comment, which is always nice, was that the bar has been raised. He's actually seen a much more careful understanding of what's happening on the site, and he can make a regulatory judgment based upon that better understanding of the conditions and the knowledge of what's going on. And I think that's it, isn't it? You know, often a regulator will say, if you can't give me a really good understanding of this site, then how can I be other than precautionary, which is a fundamental of the new Part 2A process? If you tell me you don't really understand it, then I have to be very precautionary. If you give me a really good, clear understanding of the problem, then actually I can be a little bit more adventurous and say, yes, I think that's fine now, we can stop there. Which is probably what you're hoping with my talk soon. So finally, one slide only. This one, actually, I think, was one of the bits of information fed into the DEFRA review, because this site was done some years ago. But this was actually 6 million was the first cost estimate for remediation. Came down to about 5 through the consultant working on it and saying, okay, we can do it a little bit more cleverly. We got involved, we did a new evaluation of groundwater impacts, and we brought down the price by about 1.5 million to about 3.5. And actually, when they went out to tender and the contractors bid it, they brought it down a bit further because they were dead keen for the work. But again, they delivered that work. I don't know if they made a profit or not. But there was clearly a lot of fat, if I can put it like that, in the cost estimate originally. And if you focus your quantitative risk assessment on the actual things that need to be done, you can save a lot of money. So in conclusion, I think the most important single issue in reducing remediation is better site characterisation. If you give a contractor good, high quality information, they will be able to design a solution which works and works with a good deal of confidence. If you understand the size, the shape and the composition of the beast, then you can deliver just enough work to succeed, which I think is the fundamental of sustainable remediation. Yes, it's important that we deal with the problems that our generation, our previous generations have caused before us, but let's not waste our resources on doing unnecessary things when actually we're better off leaving those resources for the next generation. So, thank you very much indeed for your time, and I hope that was of interest.
Thank you, Phil.